Hello and welcome to the 61st session of Porous Media Tea Time Talks. We are part of the Imperial Young Academy, an ambitious initiative by and for early career Porous Media researchers around the world. And we are under the umbrella of International Society of Porous Media, or Interpor. With this webinar series, we aim to give junior researchers, primarily PhD candidates and postdocs, working in diverse porous media sciences, the opportunity to present their work to the scientific community worldwide. Our vision is to level the playing field for the next generation of exceptional researchers by providing them a forum for equal opportunity exposure, encouraging interdisciplinary collaboration, and enhancing career development prospects. My name is Mohamed Nouraipur. I am a researcher at the CO2 and Hydrogen Storage Group at the University of Oslo, and I'm thanking you for joining us today. Without further ado, I would like to introduce our first speaker. Tobias Forslund is a postdoctoral researcher at the Luleå University of Technology. He's an expert in using, implementing, and developing GPU-accelerated methods for investigating transitional flow in porous media. Tobias's main focus has been accurately modeling both temporal and spatial scales of fluid motion in ordered porous media. During his postdoctoral research, he has continued applying these methods to study similar phenomena in more general packed beds. Thank you, Tobias, for joining us today. We are excited to hear about your very interesting research, and the floor is yours.
Yes, thank you very much for the introduction. So the name of my talk is GPU Accelerated Methods for Transitional Flows in Porous Media. And as mentioned, I have a PhD from Luleå University of Technology at Fluid and Experimental Mechanics, and I'm currently doing my postdoctor here. So before we get into any of the details, I would just like to shortly present our department or my subject here at LTU. So we're located just below the polar circle here in northern Sweden, and we have 18 senior staff and 23 PhD students. So we do a lot of industrial and environmental flows, and especially coupled closely to the industries that are here locally in northern Sweden. So we have a modern laboratory, the John Field Laboratory, and we have good resources for computations. So yearly we publish about 30 papers in peer-reviewed journals and 15 papers on conferences. So it's like a medium-sized department where we do a lot of stuff that is closely connected to industry. That's sort of our profile. So let's get into it. So transitional flow in porous media and how we define it. So I'm going to show an animation here where you can see sort of how the different regions of flow in porous media looks like. So furthest to the left here, you can see a Darcian flow. So I don't mention specific Reynolds numbers here because the Reynolds numbers aren't really important. You can define them however you want. The important thing is that it would increase to the right. So for the Darcian flow, the viscosity completely dominates the flow. And as you get into the laminar steady region, you have some inertial effects, but the flow is still entirely steady. So you would say that the temporal change of the velocity is zero. In the laminar unsteady region, you can see that you are getting some variations in the flow field, but the variations are fairly large in the flow field. So usually you would see one single peak in the frequency spectrum or the temporal fluctuations for this laminar unsteady case. And then in the turbulent case, the transition between the laminar unsteady and the turbulent case is not entirely clearly defined. It depends on who you ask, but usually you would say that you have temporal variation with a turbulent cascade. So essentially when these turbulent spatial scales get small enough so that they are significantly smaller than the pore size, then you would say, yeah, now it's turbulent. But before that, when it's dominated by a single large frequency, you would say it's laminar unsteady. So that's how we define transitional flow in porous media. So let's talk a bit about our approach to modeling this transitional flow. So with experimental and numerical methods. So this talk is mainly about the numerical methods, but I feel like I need to bring it up, the experimental methods as well, because a numerical method is not really useful unless you can actually validate it against something. So the tools that we have at our disposal is tomographic PIV measurements, and the rig sort of looks like this. So what you do is that you inject a bunch of particles into some fluid, and then you see how the particles move, take sequential images with these cameras, and you can reconstruct a 3D flow field from that. And then to be able to capture it accurately, you need to refractively index match the obstructions with the liquid. So we've used some mineral oil and heptane mixture to match it to quartz glass for this case. You can see sort of a CAD overview of what the rig looks like there. So similar methods is laser Doppler velocimetry, where instead of gathering a lot of data to form averages over a large domain, we look at a single point, and then we get a lot of temporal information instead, from which we can extract turbulence characteristics and so on within that specific point. So you can say that these two methods sort of complete each other in the sense that the tomographic PIV gives us a lot of average over a large spatial extent, and the laser Doppler velocimetry gives us a lot of temporal information in a single point, but no spatial distribution. So, and this can also be completed then with a pressure monitoring procedure, which we have used in this article here. You can read if you're interested in finding out more about how these experimental procedures are set up and done. So it's called non-Stokesian flow through ordered thin porous media imaged by tomographic PIV. So that's the experimental methods that we used. So when it comes to numerical modeling, we have two main approaches that we use for simulating transitional flow in porous media. So one is an artificial compressibility finite difference method. So for this method, you start immediately from the Navier-Stokes equations, but you adapt the continuity condition a little bit. So what you can see here is that instead of just using a continuity condition, we have added a compressibility factor beta here, and then we have added a temporal change to the pressure term. So this is sort of inspired from how a gas would function. So as you have a positive influx into a region or a node or a volume, you would increase the pressure in that region. And these are called artificial compressibility finite or artificial compressibility methods. And the version that I have implemented and that is available, I will show a link later as an open source project, uses central differences in an FDM environment. So this results in a spatial computational kernel that looks a bit like this. And then you can also just discretize the temporal derivative using an Euler forward for the case of a GPU, where you can use a lot of additional time steps without getting, still be computationally efficient. So one of the methods that I've been using for most of the time is so-called lattice-Boltzmann methods. So these methods start from the Boltzmann equation instead. And this looks a bit like this. And you can see that it looks a bit like a convection diffusion equation, depending on how you define this omega function to the right. And it recreates the hydrodynamic behavior as an emergent effect. So the hydrodynamic behavior is a second order effect. So usually you subdivide the computations into two steps, a relaxation step and a streaming step. So during the relaxation step, you take all the velocity distributions that you have within your current node and you sort of contract them to, or you apply some sort of operation onto them. And then during the streaming step, you exchange the information in between them. And it turns out that this procedure is really appropriate for GPU implementation, which is why it has garnered such a wide application within that community. So here you can see examples of what these distribution functions would look like in 3D for two examples. So This one to the right here is a so-called D3Q27. So it has 3 dimensions and 27 distributions. And here is D3Q7, which has 7 different values and 3 dimensions. So just some short info about GPU programming as well. So to the left here, you can see a bit of an overview of what a CPU would look like. So it would have the core and the control unit and the L1 cache. In comparison, the GPU has a lot of cores for each control volume. So that means that if we can manage to make an algorithm that makes use of doing very similar operations, then we can really use the GPU efficiently. And what you can see is that for this LBM model, it's very easy to parallelize into that situation, because what we're doing at each node is essentially exactly the same. So it's one of these embarrassingly parallelizable problems that is really straightforward to do. And you don't really need a high-end GPU to do it at all. Even though not all algorithms are suitable for GPU implementations. So those with large computational kernels or branching program structures are commonly given examples of this. So voxel solvers such as those presented here are especially well suited, since the memory can be packed efficiently and the program structure is identical for each node. And an additional perk that you get from the GPU programming is that live rendering for the visualization can be done immediately, since the data is already stored on the GPU. So this is sort of what I just said, that we can do the analysis and the rendering directly on the GPU, which we can do quickly because the GPU is a computationally efficient machine. So extracting the Reynolds stresses or other higher order moments from the simulations can be done directly on the GPU and then just saved down. So this is something that I've made use of a lot in my work. And this also yields quick simulation feedback. And here you can see an example of what it looks like, sort of the interface while I'm running my simulations. So I have this live renderer that renders the simulation results. And usually if I'm confronted with some new type of problem, I would boot this up, load in my geometry, and I would mess around with the viscosity and the driving forces and so on, and try to see what happens within this specific geometry that I'm looking at. In this sense, it's very similar to like an open source version of ANSYS. ANSYS has a similar tool. I can't remember what it's called right now. Yeah. So here you can see an example of an implementation of a dual lattice hydrodynamic thermal LBM model, and how it looks like when you're running it for a porous media. So this is a more highly resolved simulation with a thermal component. So what we're looking at here is the thermal field. And you can see that we are getting really high resolution. We can see all the vortices within the flow and so on quite clearly. And if you look up this article, you can also see that it accurately recreates the expected behavior for this type of system. So we can go all the way from like Darcian flow up until non-steady. Some people would call this non-turbulent, some people would call this turbulent, but it depends sort of on who you ask, whether the scales are actually small enough to classify it as that. So let's get into some interesting results then. How much time do I have, by the way?
You can continue to waste. No problem.
Okay. Yeah, nice. So some of it published and some of it unpublished. So first I want to talk about steady state inertial structures. So an interesting steady state inertial flow structure was discovered while we were doing this tomographic PIV experiments that I mentioned earlier. So as the Reynolds number is increased, you can see that we go from having the viscous diffusion sort of just destroying all the structures in the material up to a situation where the turbulence is just destroying all the structures in the material. And in between, we have a lot of interesting stuff going on. Especially, you can see this epsilon-shaped profiles that appear around a Reynolds number of 170 and then slowly disappear as the Reynolds number is increased. From numerical simulations, we figure out that the effect is not a wall effect, but actually a steady state inertial flow transition. And this is the sort of the model material used. So you can see a staggered cell with periodic conditions on all sides. And at a specific Reynolds number, the flow goes from being symmetrical, nice, sort of as you would expect 2D for this case, into this sort of zigzag pattern, or that is significantly more topologically complex. So the question that arises from this is, of course, is this transition specific to the staggered cylinder packing, or is it a specific example of a more general transition? What types of packing does this transition occur in? Or is there any volume average flow field quantity that characterizes this transition? So 3 different ordered packings are investigated for this. So a staggered cylinder packing, a staggered rod packing, and a staggered or a BCC packing of spheres. So they are all sort of high tortuosity packings that you would expect to, there are sort of model problems that you see popping up every here now and then. So for the staggered cylinder case, you can see that as the Reynolds number is increased, you have this cutoff point where this onset starts, or the transition onset starts. And we see that we don't have a really significant change in dimensionless pressure drop. So you probably wouldn't see this if you had like a pressure meter in your flow. So this is just something that the flow would do and you wouldn't notice, although other properties of your porous material or porous flow might of course change, such as dispersion. For the staggered rod, we actually see that we have a trend change at the break and the transition onset. So you probably would notice this if you had only a pressure monitor. And for the BCC packing, we see that we actually get 2 separate transitions. But this later one is really the one that we are interested in. Here we can also see a similar trend break to the staggered rod case. So it turned out that a reliable indicator for this change was actually the surface integral of the pressure across the solid fluid interface. So it turns out that these inertial cores really, as the viscosity is decreased, they tend to not impinge on the solid surfaces. So they tend to find alternative flow paths around those. And this strictly changes the value of this integral directly as the transition occurs. So it can be interpreted as the inertial cores no longer impinging on the solid structures, sort of the takeaway from this. And later analysis also shows that the helicity, which is a measure of the topological complexity of the flow, is also strongly related to this. But this is not something that would really be observable from you. If you wanted to look at a bed, you could conceivably see how hard the flow is pushing at your solid structures, but you couldn't really see the helicity of the flow. So, but still, the helicity turned out to be a better measure of this transition. So this is also actually published research. So you can look it up if you want to know the details of it in this article, Steady State Transitions in Ordered Porous Media. So another research direction is the interaction between large-scale flow structures in 2D and 3D porous media. So when we say large-scale flow structures, we say flow structures that are significantly larger than a single representative elementary volume. So if we would have some repeating structure throughout our domain, and we see flow structures appearing that are larger than that repeating structure, would have large-scale flow structures. And this is, of course, related to how large our representative elementary volume needs to be in ordered porous media. So these are some examples of how you can sort of place out this or tile this across 2D space. And in conclusion, we have said that, or we have come to the conclusion that the representative elementary volume has a large impact on the emergent microscopic properties. Especially these 1x1 cells turns out to be really bad when it comes to predicting behavior in the unsteady domain. And this is also explained in great detail and analyzed in the effects of periodicity assumptions in porous media modeling, which is another article that I urge you to look into if you're interested more in this. So instead of diving into sort of graphs and everything, I'm just going to show you some videos where you can pretty clearly see what these large-scale structures actually look like. So this is an example of where we have an inline arrangement of cylinders with walls on top and bottom. And what you can see is that all conditions are the same across all of these simulations. The difference is only the amount of times this representative elementary volume is tiled, so how much repetitions you have of it. And what you can see is that here at around time step 130,000, you can see that you have a trend break for the 4x4 and the 3x3 repetition. And this significantly lowers the interstitial velocity. And because of that, it also lowers the pressure drop, or the pressure drop becomes higher, dimensionless pressure drop. So this actually increases the resistance. And even though the effect is later to start for the 2x2 case, it doesn't start at all for the 1x1 case, because there's no way for a 1x1 repetition to actually represent this. And this is sort of the idea behind this. And formally, in the paper, I analyzed this using proper orthogonal decomposition. And then you can sort of extract what these different large-scale structures actually look like. But intuitively, you can understand it by just looking at these animations and saying, yeah, well, am I actually capturing all of the flow structures? These things also occur in staggered porous media as well. And you can see here, for a 4x4 repetition or a 2x2 repetition, that the interstitial velocity is significantly higher for the 2x2 case compared to the 4x4. But here it's not really as obvious what the large-scale structures are. So you can't really see them directly by looking at it with your eyes like this. So here you would need to do like some further analysis on it to actually see what is the difference between them. So I've seen some cases where people would be happy with just using like a representative elementary volume like this, but usually if you're doing temporal simulations, you should really investigate how large it needs to be. So the LBM method can also be used to resolve the flow during transition in large porous systems. So here you can see from this, so we have modeled this experimental cell that we have used in experiments earlier. And the geometry looks like this. And the different meshes that you can use sort of look like this. So the wall elements are marked in yellow, or the neighbor wall elements is marked in yellow, and the purple ones are wall elements. And you can see that the LBM method is capable of accurately capturing the behavior throughout the computational cell. So you can see that you have different behaviors close to the wall compared to far from the wall. And compare it with the experiment, you can see that we're getting similar behavior, although not exact. And I mean, measurement errors and slight inlet deviations are of course to be expected. So there is nothing strange about this. So both for the laser Doppler velocimetry and for the LBM simulations, we are getting fairly good agreement. So in summary then, with GPU accelerated methods, large data sets from sweeps can be generated. These data sets can then be analyzed either on device or saved for later analysis. The computational capacity of the GPU naturally invites studies of systems that take a long time to evolve, or statistical quantities that take a long time to gather. So the work has resulted in 2 open source solvers that are published under an MIT license, and you can find them at these addresses. They are also referenced to in my work, so you can use them. They are free to use. And then thank you for your attention, and I'll gladly take any questions. And also this research was funded by Vetenskapsrådet.
Excellent. Thank you very much, Tobias, for the excellent overview of your wonderful research. You dived into many different things, and the tools that you are using is certainly of interest for many young researchers. To keep it educational, do you have any suggestions or any recommendation from where to start if anybody is interested in GPU accelerated methods? How they should approach this kind of techniques, and how they can make progress rather quickly with implementing the directions that they want with the GPU assisted methods.
Yes, I like the idea that people should try to build things themselves from the ground up, so that they properly understand it well. And I would say that start with reading the articles on LBM that are like sort of the groundwork that was done on it, and implementing a model such as what was it called now? Then one of these single relaxation time models are really straightforward and easy, and transferring it to a GPU is not especially hard. There are some steps there in between. And I would say just read the articles and start messing around with GPU computing. And there are really good guides for CUDA and OpenCL to get started with this. And just don't be afraid to get into it. It is hard, but it is easier than you think, I would say.
And do you have any suggestions for the sources for the tutorials that our audience can go and check?
Yeah, I would need to look through my bibliography for that. But I would say, actually, Nicolas Del Bosque, I think is called, he did his PhD some time ago, and I find myself constantly referencing that. And there he really goes into detail into the CUDA programming and why LBM is good and so on. I don't know if I can write it down somewhere here or should. But, I would say that his thesis is a good resource for this.
Excellent. Thank you very much. Thank you again for joining us and for this very excellent overview of your wonderful research. Now let's switch gears and move on to the second speaker of today. Sajjad Foroughi is a research associate at the Imperial College London in the Earth Science Department. His expertise lies in the poroscale modeling, image analysis, and the application of computational methods for multi-phase flow in porous media. Sajjad holds a PhD from Sharif University of Technology in Iran. We appreciate you being with us today, Sajjad. We are looking forward to your presentation, and please go ahead and start. The floor is yours.
Thank you, Mohammed. Hi, everyone. The presentation that I would like to present today is on the work on the multi-scale pore modeling we did in Imperial College. So if I want to, the outline of the work, it would be like at the start, I present the workflow that I developed for incorporation of the microporosity or subresolution porosity into poroscale modeling. So at the first, I started with this explaining this workflow, and then I shared the result for 2 case studies. One of them is water with Stelladus sample, and the next one is a Silurian dolomite sample, and then the conclusion and future direction for this research. So we know what is porosity modeling or porosity imaging. Make it possible for us to see inside the pores and the tiny pores, and made it possible for us to do simulation on the smaller scale of the porous material. And in this research, I work on the rocks, for example. So when we do the porosity imaging, we have always a trade-off between the voxel size and field of view. If we want to see you want to fully resolve the pore space, we need to have a small voxel size, then the field of view will be small. And if we want to have a larger field of view, we have a bigger voxels and we lost a lot of features and we cannot fully resolve the pore space. So there is always a trade-off between these two. And with the microcity laboratory stuff that we have, we can get a resolution between 3 to 5 micron, not lower than this resolution. So it makes it possible, if the porous material is wide and we have a lower pore space than this size, we cannot resolve it. So there is always a sub-resolution porosity. And for some cases like Stelladus rock, which is a heterogeneous rock with wide pore size distribution, we have a huge fraction of the pore spaces unresolved. For example, in a study by Lin et al., they could just resolve by 3.58 voxel, they could resolve 11% of a sample which has a 29% porosity. So how we can characterize this sub-resolution porosity? For the characterization and for quantification of this unresolved porosity, we use a technique called differential imaging. We have a dry scan image fully saturated with dry air, and we have one again fully saturated with brine. By difference between these two images, we can quantify the sub-resolution porosity. And why this sub-resolution porosity is important in modeling is not just because of the volume, its effect on the connectivity, accessibility, and if we don't consider them in the modeling, the model will have we cannot see the actual image and actual pore space connectivity. So the goal of this study is to incorporate this sub-resolution porosity in our modeling. So this is the general workflow of the work. So I show here the one slice of the dry scan. So by dry scan, we can do segmentation and we can see the pore space. At the same time, if we have a same rock fully saturated with 30% Ki brine, we can see the sub-resolution by differential imaging, and we can segment the voxels that contain sub-resolution porosity. And then from the result pore space, we can, like traditionally what we do pore network extraction, and we extract it as a network of pores and throats. But with the new workflow that I am presenting here, we include this sub-resolution porosity as a new type of element that we call it microlinks. So the development of this workflow, we need to, as I said, we need to include this sub-resolution porosity as a microlink into our pore network modeling. For this, we developed an automatic dilation algorithm that find each voxel with sub-resolution porosity that the two nearest pore to this sub-resolution voxel. So all of this process is done by automatic dilation algorithm. It's like a learning algorithm, and we assign 2 pores to each micropore, which is the nearest pore. All of the microporous voxel with the same pair of the pores belong to the one microlink that connect these 2 pores to each other. So then it's the process of the microlink is presented here. So for example, how is dilation algorithm work? And this is 2 pores. This is the microporous region between them. and we assigned nearest pore and then the next nearest pore, and then by combining we can find a microlink between two pores, and this schematic for the case that we have a microporous region between three pores, and we find 3 microlinks between these 3 pores. So after the characterization of the microlinks in terms of topology, we can include it in our network. Here is the network, as I said, from the result pore, and here is the multi-scale network. Then after the characterization of microlink topologically, we need to assign to them the length, area, volume, because this microlink is a Darcy type element. It's not like a result pores and throat that they have actual length throat area. So we calculated from the differential imaging result. Differential imaging provides us the porosity map. So from porosity we can get volume, and from volume and the distance we can get length, and we assign area to this micro and also porosity to these microlinks. And then we assign the single phase property. For the single phase property, I mean conductance, permeability, we use the Cousins-Kalman equation. And for the two-phase property that for the microlink we require, we use the empirical model to assign to them saturation and conductivity and capillary pressure. After this, we need to modify our flow model to include these new microlinks, and then we validate our result against the experimental result that we have. So the challenge that we have is the computational challenge that we have. One of the challenges, the problem that we work with a big image. So in this big image, we need to do the dilation algorithm to find the nearest pore and next nearest pore. And this, because this image is 3-dimensional, 1000 by 1000 by 1000, it's really big image. We need to do it in the parallel. So we decompose our pore space to subvolume and then do the dilation algorithm on the subvolumes. And also another challenge is physical challenge that we have is that when we have 2 microlinks connected by a pore, we should be able to have a bypassing of the pore, because in some scenario the pore, for example here, pore J can be filled first, and when this fills completely filled, it can hinder, it can stop the flows through the microlinks. To stop this, to bypass, to let the flow bypass this pore, we use this condition for the conductance of the between 2 pores. As I said, for the microlink, we need to assign the proper physical property like volume, area, porosity, and permeability, which I show the relation here that we use. This the main source of this parameter is determined from the porosity map, which determined from the differential imaging. And also for two-phase property, we use leverage J function as a two-dimensional the capillary pressure, and then for the J function that we have, for drainage we use the Paula model, and for the water flooding part we propose a tangent function model that can capture the capillary model that we expect in the water flooding. Then it can handle different type of wettability. And for the conductance of the microlinks, we use the Paula model, and for the resistivity, we use Archie model. So here I show the result, the shape of the capillary pressure and relative permeability model. Here the drainage from the Paula model, and the capillary model came from the proposed model that we, the reference for this at the end of the presentation I will show. Here is the capillary model for different in start of the saturation in the microlinks based on the tangent function model. And this is the result of the relative permeability, but we consider the kilo model to see the hysteresis. Then when we developed our workflow, we applied to one of the case study, which is water with Stelladus sample. This Stelladus sample done by Yin Ga. She did two samples, one of them water with sample, one of them with a higher capillary, which has intermittency effect, and one with a lower capillary. I used the lower capillary without the intermittency effect, and it's because it's a water wet, it's the perfect case to check our work, to check it out for our work. So if I can show here is the result of the porous size distribution for the Stelladus and for two other samples. So as I said, for the Stelladus, we have a wide pore size distribution. So for example, here is 3, if you consider 3.58 here as a result, huge fraction of the pore space is on result. The Stelladus is below here. So for this case, this Stelladus case, the helium porosity is 30%, the result porosity is just 10%, and huge fraction of the porosity is unresolved. So, and this is the porosity from differential imaging. So you can see the differential imaging can get similar result to helium porosity, which show that the potential of the differential imaging. So we select 3 subvolume from this sample, with the size of 1,127 by 1,000 with cube of this sample, 3 subvolume, and we run the pore network modeling without considering the subresolution porosity and with the multiscale pore network. Here is the subvolume 1. For example, you can see that the porosity, this is the result porosity, and after including the subresolution from differential imaging, this is the porosity from the multiscale pore network. And also this is the permeability from the multiscale pore network, and this is the result of permeability without considering the microlinks. You can see that the permeability is 1 order of magnitude lower than the experimental value. So if you want to be able to match the permeability from experiment, we need to include the microporosity or subresolution porosity. Same for formation factor. Here the formation factor is huge, which means it's wrong, it's not connected, the connectivity is poor. And we know the actual formation factor should be much lower, and this is the result from the multiscale, which is much closer to what we expect for a Stelladus rock. Same thing for the other subvolume. So for the next stage, for the single phase, we showed that the multiscale present very well when we apply for the Stelladus. The next is to see the behavior for the two-phase flow simulation. In the case of two-phase flow simulation, we noticed that we need to consider 2 types of microlink, because if you can see here this 3.58 resolution, we can see that not all of the unresolved pore space is microporosity. Actually, it is 2 types of microporosity we need to consider. One of these unresolved macroporosity, and one of them is microporosity. So we consider 2 types of microlinks, and depend on the porosity of microlinks, we assign different grain diameter, which affect the permeability of microlink from the Coulson-Kallman equation. But to be able to match the capillary here, we define a smooth transition. It means we don't use a specific criteria to define those microlinks. We use a normal distribution to find a critical value to classify these microlinks. So here is the result of the MICP, capillary pressure from the literature data for Stelladus, and here is the result, also the result of the capillary pressure from the model, multi-scale model, MICP. So you can see that the model can be able to match the MICP result very well for all of the three subvolume, and this shows the potential for two-phase flow of the model. Here is the result of the prediction of the result of the relative permeability for 3 subvolume. we don't have the result for experimental result for this subvolume, but their behavior is in line with what we see in the literature. So, and then the result of water flooding for the Stellades, it is the result of first subvolume, this is second subvolume, and this is third subvolume for relative permeability. Relative permeability is an important parameter for us, and we can see that all of the experimental result match modeling result match very well with the experimental result that we have. So we could be able to validate our workflow and our multi-scale pore notebook for this Stellades sample. The next sample that we want to apply is a Silurian dolomite sample. For this sample, we don't have any experimental result regarding two-phase flow. So we just predict what would be the result if based on our multi-scale pore notebook model. This Stellades sample is similar to the previous one. Permeability is like 350 millidarcy. Based on different subvolumes that we have, and this is from provided by Shell for us, and this is pore size distribution. We can see here as well. We have two peaks which show it's a microporous rock, and because of the we consider voxel size here, for example, we can see we need to consider two type of microlinks for this case sample as well. MICP also provided. So we took this image. This is micro core, and this is a miniature core with 20 millimeter length and 6 millimeter diameter. And we did one dry scan, one fully saturated brine, 30% Ki, and we could be able to do the differential imaging and extract the porosity map. At the same time, permeability from experiment that we did is like 200 millidarcy. So it is the result of permeability from provided by Shell for us, the laboratory in Shell, and this is from the subvolume of that sample, which is the smaller part of the sample, is more or less same in the same range as the bigger sample. So we select 5 subvolume from this sample, which with the size of 1,000 cube. The voxel size for it is 3.95, and the porosity, helium porosity, 23%. So here is the result of the subvolume. This is the result of differential imaging porosity, and the differential imaging porosity is more or less same as what we see in the helium porosity measurement. This is the result of pore size distribution for resolved pore, and also this is the result of permeability by multi-scale pore network modeling. We can see that here the result porosity is like half of the pore space is resolved. Is not as like Stellades. We can resolve more pore space, but still result of permeability is lower than what we can get from the multi-scale, and also lower than the experimental result. Same as formation factor. Without considering microscale, formation factor is much larger than the formation factor when we consider multi-scale, which is more in line with what we see in the literature for formation factor of this type of rock. And this is the result of the MICP for this subvolume, and this also result of capillary pressure for this subvolume. So in here, same as the previous case, we defined 2 types of microlinks with the soft criteria to have a smooth transition between these 2 regions. So we could be able to get the same behavior as MICP. This MICP is exactly the same rock, but this MICP of other sample rock is more or less similar. But we can see that the model can catch this smooth transition between different behavior that we have for the capillary pressure. So Here is the result of the relative permeability. This is the predicted result for this 5 subvolume. And as I said, we don't have the result of the experimental result, so it's just prediction. And the last case is that what will happen if we change the saturation in the start of water flooding for this subvolume. We change the start of water flooding from 25% to 45%, and we can see the relative permeability for different initial saturation. So in our workflow, we'll be able to develop this multi-scale pore modeling. We tested against Stelladus rock with experimental result. We could be able to match the result of the relative permeability by calibration against the permeability, formation factor, and capillary pressure. And we applied for the different rocks, silver and dolomite. We could be able to match the capillary pressure, and we predict the result of relative permeability. And currently, what we want to do is we want to see the effect of wettability on the relative permeability by this multi-scale pore model tools that we have, and then we want to apply for other samples that we have in our project. So at the end, I would like to thank Shell for the support of this work, and here is the thank you for your attention. Here's the reference and also our GitHub for the code and for the paper.
Excellent. Thank you very much, Sajjad. It was really exciting work and well done. Just to clarify, these references 1 and 2 are the published work based on the presentation you gave today, yes?
Yes.
Yeah, excellent. Very well. We have a question from Said Sadeghnejad. He's asking, Sajjad, thank you so much for your nice work and the presentation. How do you determine the microlinks diameter when an unresolved porosity is shared among various pores?
Thank you, Said. That's a great question. For the microlink, as I said, we defined as a Darcy type element. So for the Darcy type element, we don't have a parameter for diameter of the microlink. We use the Cousins-Kalman to determine the permeability, and we use the porosity from porosity map derived from the differential imaging to determine the porosity of microlinks, and then from the porosity we can determine the permeability of the microlinks, and then the permeability used in our pore modeling.
Excellent. Jumping on Said's question, in some of the reactive transport model studies that we perform, sometimes we have evolving porous media, either because of the dissolution and precipitation, and in many of them we are always dealing with the unresolved porosities. And based on the measurements and also based on the simulations, we know that the Cousins-Kalman will not work for such a system. Do you have any suggestion how we can use multi-scale PNN and the approach that you are developing fitted for the reactive transport modeling in the evolving geometries?
Yeah, thank you. That's a great question. For the evolving geometry, if we can see the pore space, so then we don't need the relation for the micro, if we can see the pore space, we can resolve it, then we can extract it and we can have diameter and parameter for the element. But if we don't have, we need to define consider empirical model for the microlink to relate the microporosity to the conductivity. So it could be the Cousins-Kalman, but you can change it, which relation that give you at the upper scale, at the upper scale result, match the capillary pressure and also formation factor and permeability. You can change and tune it based on the parameter that you have in our microlink model. It can be Cousins-Kalman, it can be any other model.
Excellent. Yeah, thank you very much, Sajjad. Thank you again, Sajjad and Tobias, for joining us today. Now let's wrap up this session, and I would like to introduce our speakers for the next session. We have Arone De Luca from Milano, from Milan Polytechnic University in Italy. He's going to talk about mixing porous media, reconnecting with spreading. And also we will have Mahsa Shirazi from the Department of Chemical and Petroleum Engineering in the Sharif University of Technology in Tehran, Iran. They will give their talks on October 15th at 3:30 Central European Time. And we would like to invite all of you to join those talks. This is the Porous Media Tea Time Talks team, and we are organizing this webinar series every month. If you would like to be part of our webinar, and if you feel that you are having a wonderful research that should be shared with your peers around the globe, drop us an email, and we will contact you, and we will try to organize a session for you. Thank you for joining us today. Thank you, Sajjad and Tobias, and thank you everyone for being with us. Have a nice evening, and ciao.